For an AC circuit with an applied voltage of V0 sine omega t and an inductor of inductance L, and I'll just emphasize this is just an inductor of inductance L, that was actually the voltage difference across it. What we found was that there was a relationship between the applied voltage amplitude and the responding current amplitude, I0, of V0 was equal to XL I0, where XL, the inductive reactance, is equal to omega L. We could divide both sides of this by root 2. Again, V0 over root 2 is VRMS, and I0 over root 2 is IRMS. So we could also say VRMS is equal to XL IRMS. So we get these very, very Ohm law looking like equations again that now apply for the inductor. But one more thing I want us to keep in mind, and that has to do with the results that we found over here. The current, now this delta I over delta t, this is a graph of the change in the current, but remember this is also the same phase as the voltage from the power supply. Our current then looks like this relative to the voltage. Notice the peak here comes after the peak from the voltage. So in this case, the current in the inductor actually lags behind the current, the voltage supply, the voltage source. So in this case, if the voltage is up here, the current in the inductor is behind the voltage, and it lags behind the voltage. Remember, the current in the inductor led the voltage, but the current in the inductor lags or is behind the voltage. Again, by how much in this case? Remember, 1/4 of an oscillation. If one complete phase is 2 pi radians, 1/4 of that, half of that would be pi, 1/4 of that would be pi over 2. So in this case, the current is behind the voltage by pi over 2 radians. The current in the capacitor was ahead of the voltage by pi over 2 radians. Very, very good. Let's stick some numbers in all of these equations. We've got a lot of equations, but they're really, some of them are very, very similar to each other. Let's stick some numbers in and see what we get. Let's imagine we have an AC circuit with a power supply with a voltage amplitude of 110 volts and a frequency of 60 hertz. And let's imagine we have it connected to a resistor all by itself of 25 ohms. Let's imagine we want to figure out what is the RMS current, IRMS. We've got two equations that we could use. V0 equals R I0, and also VRMS is equal to R IRMS. Let's use the first one. So V0 equals R I0. In other words, I0 is V0 over R. I0 is V0 over R, which is 110 volts divided by 25 ohms, or 4.40 amps. That is I0, the current amplitude. To find the RMS current, IRMS is I0 over root 2, or 4.40 amps over root 2, which leaves us with IRMS is 3.11 amps. We could do this a slightly different way and use the second equation. We know VRMS is R times IRMS, where VRMS is V0 over root 2, which would be 110 volts divided by root 2, which is 77.8 volts. And then IRMS is VRMS over R, or 77.8 volts over 25 ohms, which again gives us 3.11 amps. So there are a couple different ways to do it. We could either use V0 and R to find I0, and then I0 to find IRMS, or we could use V0 to find VRMS, and then VRMS equals IRMS to find IRMS. Okay, very, very good. What about a capacitor? Let's imagine now we have a voltage source with a voltage amplitude of 12 volts. Again, a frequency of 60 hertz. And now a capacitance of, let's say, 2.40 microfarads connected all by itself. And again, let's imagine we want to figure out what's the IRMS for this circuit. Again, we have two possibilities. We could say that V0 is XC I0, VRMS is XC IRMS. But for either one, we need to figure out what the capacitive reactance is, and for that we need the value of omega, not the regular frequency, but the angular frequency. So let's figure that out. Omega is 2 pi f, or 2 pi times 60 hertz, which is 377 radians per second, or remember, just kind of ignoring that unitless unit of radians, we could just say inverse seconds. And then XC is 1 over omega C, which is 1 over 377 inverse seconds times C, 2.40 microfarads, putting that into standard SI units, 10 to the minus 6 farads, multiplying that out, and we get 1,110, and remember again the units, ohms. We could do this either one of these ways. I naught is V naught over XC, which is 12 volts over 1,110 ohms, which is 0.0108 amps. The RMS value is the amplitude over root 2, or 0.010 amps divided by root 2, which is 7.64 times 10 to the minus 3 amps. Or VRMS is V naught over root 2, 12 over root 2, which is 8.49 volts. And then IRMS is VRMS over XC, 8.49 over 1,110 ohms, which is 7.65 times 10 to the minus 3 amps. Notice, this is only slightly different than from this one. Why? It's just a rounding error. Don't worry about that sort of thing. That last decimal place is just off just because of how these numbers were rounded. Often if I do these, I'll leave the number on my calculator. I might just take 12, for example, I might take 2 pi times 60 and get 370 whatever. This might actually be 376 point something something. Actually, I think it is. And then when I want to calculate x of c, I might just leave that on my calculator, multiply it by c, and then take 1 over that and get this number, and just leave the number of sig figs, and then only round it at the very, very end for whatever number of sig figs I need for my final answer. Or you could do it as you go along. I think it's easier to just leave the number on the calculator rather than constantly putting it in over again. Yeah, I think you make fewer mistakes that way. Anyways, there we go. There's the RMS current. What about if we have an inductor by itself in the circuit? Now let's imagine we have a voltage source, an AC voltage source, with a voltage amplitude of 15 volts at a frequency of 75 hertz, with now an inductor with an inductance of 0.265 henries. And again, let's imagine we're looking for the RMS current. We might not always be looking for the RMS current. Maybe we'll be looking for something else, but let's just imagine for these, we're always looking for the RMS current. Again, we could use that V naught was equal to XL, in this case I naught, or VRMS is equal to XL IRMS. Again, to figure out XL, we need omega, so let's do that. Omega is 2 pi f, 2 pi times 75, which is 471 radians per second, or inverse seconds. X sub L is omega L, which is 471 times 0.265 henries, or 125 ohms. Two different ways again. I naught is V naught over XL, which is 15 volts over 125 ohms, or 0.120 amps. IRMS is I naught over root 2, 0.120 amps over root 2, or 8.49 times 10 to the minus 2 amps. Or we could use VRMS as V naught over root 2, 15 over root 2, which is 10.6 volts, and IRMS is VRMS over XL, 10.6 over 125 ohms, 8.49 times 10 to the minus 2 amps. Again, exactly the same thing. Very, very good. Let's recap what we've gotten today, because we're going to use this as our starting point for the next time, and I'll explain why in just a second. In summary, what did we find today? If we have an AC circuit with a power supply with a voltage of V naught sine omega t, if we have a resistor all by itself connected to the power supply, we find that the current in the resistor had the form of I naught sine omega t. And I'll come back to this I naught in just a second. If we have a capacitor all by itself connected to the power supply, we found that the current in the capacitor had the form of I naught cos omega t, which we could also write as I naught sine omega t plus pi over 2, because we saw that the current led the voltage by pi over 2. If we have an inductor connected to the power supply all by itself, we found that the current in the inductor had a form of minus I naught cos omega t. Or we could write that as I naught sine omega t minus pi over 2, because we saw the current in the inductor was behind or lagged the voltage by pi over 2. Talking about those phases, and those phases are going to be important next time, and I'll explain why in just a second. The current in the resistor was in phase with the voltage. In other words, voltage, current in the resistor, they oscillate together in phase. The current in the capacitor leads the voltage by pi over 2. This plus pi over 2. The voltage, the current in the capacitor leads the voltage. So the current in the capacitor is always in front of the voltage. For the inductor, the current in the inductor lags, meaning behind. It lags the voltage by pi over 2 radians. We have this minus pi over 2 over here. So voltage, current in the inductor, it's behind the voltage. So the current always is behind the voltage. The current in the inductor is behind the voltage. It lags the voltage. Very, very good. And then we have some, back here. And then what about those amplitudes? We know that for the resistor, V naught is R I naught, or Vrms is R I RMS. And then for the capacitor, we have a very similar looking equation. Looks a lot like Ohm's law, but rather than the resistance, we have the capacitive reactance. V naught is XC I naught, or Vrms is XC I RMS. For the inductor, we have the inductive reactance. For the inductor, V naught is XL I naught, or Vrms is XL I RMS, where, let's remember, omega is 2 pi f, the angular frequency is 2 pi times the ordinary frequency. XC, the capacitive reactance, is 1 over omega c, where c is the capacitance. And XL, the inductive reactance, is omega L, where L is the inductance. Very, very good. Remember, today we looked at a resistor by itself with the power supply, a capacitor by itself with the power supply, and an inductor by itself with the power supply. Next time, we're going to put all three together in series with the power supply, and we will see how they interact with each other. And these phase differences are going to be very important in our analysis. Well, I hope that was interesting. I hope it was fun. I really enjoyed this stuff. I'll see you next time.